here studying so-called Sylvester method. So what they are trying to do is power the complex that analytic function, analytic means.
Hocam kamera kaldı.
Evet, fark ettim. Function itself. And we would like to compute operator, and let's say the dimension of B is N, and we would like to compute f of A. This is by definition just.
Hocam kamera diğer tarafta.
Biri almıştım. Evet, 3'le bir yer değiştirmiş. Pardon. Demin yaptım bunu. Evet, yanlış. Suppose f of a is so f of a is defined this way, a to the power, and we'd like to compute this infinite sum, and Sylvester is the following. What we have done last time was the following. If okay, so let's say the characteristic polynomial of this is let's say g of x, characteristic polynomial, and suppose that it has distinct roots. Suppose g of x has distinct roots like this. As distinct roots. Then we have seen the following. Ya aslında şöyle, karakteristik polinomial is something like this, right? So ben bunları a yazdım, değil mi? Yani minus 1, a of x, a0.
Evet, ama karşımasını yani. Aslında sikal yapmıştık.
Efendim?
Karşımasını sikal yapmıştık.
Bunları nasıl sikal yaptık? Şöyle. This is the characteristic polynomial. So when I plug from K to Hamilton, when I plug x equals a, then we get 0. So a to the power n, just a1, a to the power, no, a n minus 1, a to the power n minus 1, up to a1 a plus a0 plus I1 is 0. From this, we see that a n is just minus a n minus 1, a to the power n minus 1, and so a1 a minus a0 plus I1. So by just plugging a to the power n into this formula for powers larger than n, we can get rid of all the higher powers of a. Therefore, this thing will be just a polynomial of a up to of degree at most n minus 1, right? Bunlara da yaklaşık şey demiş miydik? Burada P demiş. Bu ne? P and minus. So this is P of A, where P of X is a polynomial of degree at most n minus 1. So P0 plus P1 X, P1 minus 1, X to the power n minus 1. Here, using this relation, I can just replace higher powers of A with lower powers, so that there will be only A squared, A cubed up to A to the power n minus 1 in this expression. Therefore, we will get a polynomial of A of degree at most n minus 1. So, this gadget is equal to P of A, right? P of A for some polynomial. And computing this infinite series reduces to computing these coefficients. And Sylvester method gives us a way of computing these coefficients. And we have seen one instance of that. Namely, the case where the characteristic polynomial has n distinct roots. So if it has n distinct roots, then we have seen that this P of X, so if P of X, which is just the determinant of this, is has n distinct roots, then we have seen that P of X is just the polynomial interpolation of f of x at the point made of lambda 1, f of lambda 1, up to lambda n, f of lambda n, where lambda 1, lambda n are the distinct eigenvalues, right? This characteristic equation has n distinct roots, means it has n distinct eigenvalues, and lambda 1 to lambda n are the values of f. So we have something like this. Let's say lambda 1 is somewhere here, lambda 2 is somewhere here, lambda 3, lambda I, lambda n, and f takes these values, let's say, and suppose this is the function f of x. What is P of x? P of x is just the degree n minus 1 polynomial interpolation of f. So it is the unique polynomial that passes through these points. Okay, there is a unique polynomial of degree n minus 1 passing through these points, and f of a becomes just P of a. Okay, actually, in this case, we had a formula for PA. What was it? Bunu da yazmıştık değil mi? Indeed. P of X neydi? Mesela şeyse evet, f of lambda var değil mi? Sonra x eksi x2 değil mi? Şöyle gidiyor. x minus, pardon, x minus lambda 2, lambda n divided by lambda 1 minus lambda 2, lambda 1 minus lambda n, and then plus up to f of lambda n, and here I have x minus lambda 1 up to x minus lambda n minus 1, and here I have lambda n minus lambda 1, lambda n minus lambda n minus 1. Right? Burada hangisini kullanıyorsun? If you have lambda I here, then you don't have lambda I here. You have all the other terms, and you have lambda I here. So the mid term here, maybe I should write the term f of lambda I, and then x minus lambda 1, x minus lambda I. This term doesn't appear, right? X minus lambda n. Böyle şapka koyunca bu yok demek. Right? When you put the head, this doesn't appear. And then we have lambda I minus lambda 1. Here, lambda I minus lambda I. But this doesn't appear. And then lambda I minus lambda. Ya aradaki geneltelim. Bu ilk durumda. So this was the first case we found so this polynomial. The second case is the following. Instead of characteristic polynomial, we can actually do the following. Theorem 2. This was theorem 1. Theorem 2 is the following. Suppose that linear transformation and from B to B satisfies a polynomial relation Q of raised to 0. This is not necessarily the characteristic polynomial. Okay, just in the polynomial. And assume that this polynomial equation, so when I plug x here, has all distinct roots. Lambda I from 1 up to, let's say, L. Okay. So it doesn't have to be the eigenvalues of the operator, okay, and the number of roots doesn't have to be well, actually they have to be eigenvalues anyway, but the number of the roots doesn't have to be n. Yani mesela şöyle düşünün, this might be the minimal polynomial of the operator, so its degree might be much lower than n. Değil mi? Diagonalizable olduğunu düşünün. vector uzayı, the vector space may have dimension 6, but the minimal polynomial may have only 2 roots. And in that case, this will be just, let's say, x minus lambda 1 times x minus lambda 2. Right? Have this thing roots. Then an analytic function f of a can be computed as f of a equals p of a, where the statement is the same. P of x is the interpolated polynomial of q of x, pardon, f of x, at the points lambda 1 up to lambda. And statement is the same. The difference is that this doesn't have to be the characteristic polynomial. It can be, for example, the minimal polynomial. Therefore, you have probably less roots. Therefore, P of x will be something of a smaller degree. So the computation could be easier, değil mi? Yani 6. dereceden bir polinomla çalışmak yerine 2. dereceden bir polinomla çalışabilirsiniz. O da kolaylık sağlar. Yani illa karakteristik polinomla uğraşmanız gerekiyor. Let's see the proof of this. Last time we had proved, the first theorem. So, okay. The polynomial x is defined by substituting x to the power of k with k larger than L through lower powers of x for x using the equation P of x equals 0. İsterseniz let me just explain this on an example. Okay, so what's going on? Suppose our operator A is something like this, and g of x is atıyorum şöyle bir şey olsun. X minus 1, x minus x plus 3 squared and x minus 2 cubed. Okay, and q of x, suppose it is diagonalizable. If it is diagonalizable, the minimum polynomial will have degree 3, and it should be just x minus 1, x plus 3, and x minus 2, right? Minimum polynomial should be this. And when I plug a here, it will be 0. Okay, so Q is this. You see, this is just what? This is x'in çarpı nedir bu? X kare artı x eksi 6 değil mi? Bu da x küp eksi x kare var. Artı x kare 0 oldu. Eksi 6x eksi x eksi 7x artı 6. So, what is the equation A satisfies? A cubed minus 7a plus 6 times I is 0. Therefore, a cubed is 7a minus 6 times I. So, in the power series, that I want to compute f of a is what? A to the power k, right? So this is just a0 times I plus a1 times a2 times a squared, a3 times a cube, and so on. So whenever I see a cube, I'll just plug this. That will be a to the power 4. For a to the power 4, I will write it like this. And then plug this gadget here, I will get something with a squared and so on. So at the end, this will be just a polynomial of degree 2. So it will be something like this. P0 times identity, P1 times a, P2 times a squared, right? At the end, this is what I would get. And my aim is to compute this P0, P1, and P2. Okay, so that's what we are trying to do. Anlaşıldı mı? Yani yapmaya çalıştınız. Bunu bir öncekinden tek farkı şu. Daha önce şu polinom kullanmıştık. Bu 6. dereceden de. Dolayısıyla hani işler çok daha uzun olacak. Peki ispata dönelim. In this case, in our examples, L is 3, right? This L is 3. It's a polynomial of degree 3, right? L is 2. And it's 6. So it's a 6-dimensional vector space, but the minimum polynomial or the polynomial they are using is often with. Tabii her polinom A'yı 0 yapan her polinom minimum polinoma bölünmek zorunda olduğu için değil mi? Minimum polinom oydu. A'yı 0 yapan her polinomu bölen polinomdu. Dolayısıyla en küçüğü bu zaten. Daha küçüğü yok. Evet.
Minimumda kare şey olabilir.
Olabilir.
Öyle olursa riskli.
Bu örnekte olamaz. Karakteristik mecburuysa minimum polinomu x eksi 1 içermek zorunda, x eksi 3, x artı 3 de içermek zorunda, x eksi 2 de içermek zorunda. Yani minimum polinomun kökleriyle karakteristik polinomun kökleri aynı.
Yani
ama mantıksızlar var. Yani şu minimum polinom olamaz.
Hocam peki şeyin minimum polinom olması nereden bileceğiz? Artık pi karesi.
Olabilir. Ben dedim, hani bu olsun. Esüm edin. Tabii bu eğer şöyle olsaydı o zaman bu 4. derece şey.
Hocam diagonalize olmak zorunda değil mi burada?
Yani o zaman tabii bu polinomu kullanamaz. Yani burada distinct olmayacak.
peki herhangi bir minimum bölünmesi gerekir mi?
Evet. Evet. Onu ayrıca. Okay, so let's do this. Consider. Başka soru var mıydı? Any other question? Sanki birisi bir şey sordu ama vazgeçtim.
Hocam ben diagonalizable olmak zorunda mı diye sormuştum orada.
Yani bu durumda olmak zorunda. Neden? Because if there is a polynomial which makes a zero and if it has distinct roots, then the characters, the minimal polynomial should have distinct roots. Yes, I mean, it should be a power of, distinct linear factors, but that should be diagonalizable. So this second theorem also is applicable to diagonalizable operators. Okay, so consider the operator another operator A1 from given by A1 is just lambda 1 times B. So just actually lambda 1 times identity operator. Değil mi? Identity değil, lambda bir başka bir şey. So this is just the constant multiple of identity operator. This operator satisfies this gadget A1 equals 0 because lambda 1 is the only eigenvalue of this operator. Daha doğrusu şöyle, yani Qx, why is this? Because Q of x has this factor, x minus lambda 1 times something, let's say R of x, and therefore, and hence, what is Q of A? It is just A minus lambda 1 times identity times R of A1, but A1 is just this gadget, right? This is just A1. Therefore, this is just here. Peki, buradan ne çıkar? So, for f of A1 is simplified by K polynomial Q of A1. Why is that? Because I know that this thing is just here Q of A, right? F of A is equal to Q of A, and here the only thing we used is that Q of A is 0, right? The only thing we have used is this information. Now, Q of A1 is also 0. Therefore, I can write A1 here and write A1 here. A1. So I will just get this. Okay. Therefore, f of a1 is the same as q of a1. Okay. Yani A için bunu biliyorduk ama A1 için de geçerli. Buradan ne çıkar? However, f of a1 is simply the operator is simply what? A1 is just serious. A1 is what? It is just lambda 1 times identity. Okay? A1 is just A1 lambda 1 times identity. Therefore, what is this gadget? This is just a k lambda 1 times identity to the power k. K from 0 to infinity. What is this? Powers of identity is just identity. I have just lambda 1 to the power k. So that is just equal to that just right here. So f of a1 is just I can just pull out identity and then I will have a1 ak times lambda 1 to the power k. So this is just ak times lambda 1 to the power k summation from 0 to infinity times identity. But what is this? This is just f evaluated at lambda 1, right? F of x is just f of x is just ak x to the power k. F of lambda 1 ak times lambda 1 to the power k. So this thing is just f of lambda 1 times identity operator. So what we have seen is that okay. So ne elde ettik bu arada şimdi? Implies therefore lambda 1 equals pure lambda. The same thing here, of course, is valid. Actually, I have this times identity, but you know, this is the identity operator. This is possible only if its coefficient are the same. Yani identity matrisi bir katı, identity matrisi başka bir katı eşitse o katlar birbirine eşit oluyor. Of course, this is true for lambda 1 and therefore for lambda 2 and lambda 3 and so on. In general, similarly, of lambda I equal to Q of lambda I for all I plus 1 after. Therefore, what is this polynomial? It is just the polynomial interpolation, not n up to L. It is there are only L many roots. So P is just the polynomial interpolation of F at the points lambda 1 up to lambda L. Hence, P of x is the unit polynomial interpolation of f of x of degree R minus 1 at the points, lambda 1, f of lambda 1, up to lambda L, f of lambda. Tamam mı? Yani aynı statement, sadece diyoruz ki karakteristik polinom diyelim. So the same statement with theorem 1. The only difference is that you can work with the lower degree problem.
Hocam yukarı tekrar gösterme şansınız var mı?
Efendim?
Yukarı tekrar gösterme şansınız var mı?
Var. Okuyayım mı? Hence Px is
Tamam
the
hocam.
polynomial interpolation of f of x of degree L minus 1 at the points lambda 1 f of lambda 1 up to lambda L f of lambda L. Tamam mı?
Tamam hocam yazdım.
Actually, proofs are in the book, but I'm just giving you more explanation. So the question is now, what if no such effects exist? Yani bu ne demek? Kökleri farklı olan, değil mi? Bir tane polinom yoksa A'yı sıfır yapar. Yani o da ne zaman tabii ki A diagonalizable değilse. In other words, what if A is not diagonalized? Okay. Peki, bakın. Babası kenarı bir yazayım. Yakışıyor. Suppose that Q of X is some Q of X is something like this. X minus lambda 1 to the power and 1. X minus lambda k to the power of lambda L to the power and n. Okay. So here mi's are not necessarily 1, so they can be higher powers. Okay. What we will do? Okay, let's see what we can do in this case. Aslında bu şuna benziyor. This corresponds to the following actually situation. If I tell you, find a polynomial function that passes through these 3 points, let's say. Degree 3 polynomial that passes through these 3 points. You can find it uniquely, right? Degree hatta degree 2. Degree 2 polynomial passing through these 2 points. Because degree 2 polynomial means you have only 3 coefficients, right? And each here, let's say lambda 1, lambda 2, lambda 3, each point gives you an equation. So this is lambda 3, lambda 1, lambda 3. So you just plug these numbers into this and obtain these equations. P0 plus P1 lambda 1, P2 lambda 1 squared is just bunlara istersen isimler vereyim. P vereyim de ne diyelim bunlara? Y1 yok bu Y2, Y2, Y2, Y1. Dolayısıyla bu Y1 eşit. P1 lambda 2, P2 y2, and then P0 plus P1 lambda 3, P2 lambda 3 squared, y3. You can solve this equation uniquely because the coefficient matrix is just the one-dimensional matrix, and the coefficient matrix is 1, lambda 1, lambda 1 squared, 1, lambda 2, lambda 2 squared, 1, lambda 3, lambda 3 squared. And this is invertible because these are different. But if I give you this problem, I gave you, suppose that I give you only 2 points. Number 1 and number 2. But again, we will have 3 equations as follows. Suppose that it has value y1 here, it has value y2 here, but then I also give you the slope at this point. I tell you that this gadget has slope like this at this point. Yani ne istiyorum ben? Öyle bir şey istiyorum ki fonksiyon bir noktadan geçecek, bir noktadan geçecek ama bir noktada da bu olmaya teğet olacak. Right? So I am looking for a function which passes through this point, and it will be tangent to this line at this point. So something like this. Okay. Although there seems only 2 points, there are 3 conditions. What are they? So this is, let's say, P of x. So P of this is P0 plus P1 x plus P2 x squared. So what are these conditions then? Let's suppose that this slope is just S1, slope with S1. So this is y, 1 over y prime. To just P1 plus 2 P2x, right? So what are the equations then? Y1 is equal to P of lambda 1 gives me this. P0 plus P1 lambda 1 plus P2 lambda 1 square, and this is Y1. And then I have Y2 equals P lambda 2. That gives me P0 plus P1 lambda 2 plus P2 lambda 2 square equals Y2. And then I have this derivative condition. P prime lambda 1 is equal to S1, right? And this gives me what? So in this polynomial, I just plug P1 plus 2 P2 S1 equals lambda 1, sorry, equals S1. So again, we have three conditions, okay? So this situation here corresponds to this geometric problem. Okay, and I'll talk about it in the next hour.